Okay. Now, today we will talk about matrices, the second topic. I mentioned before that we have 3 topics to cover this semester. We finished the first one, which is vector calculus, integration and differentiation of vectors. And then the next topic, which we just started, we need maybe 4 to 5 weeks at least to finish this topic, which is related to matrices, which I'm sure you will enjoy this topic. It's really interesting and related to many engineering applications in different specialties. And then the third topic will be the differential equations. My advice, always look to the history, from where it came, the topic itself, and when you finish, look to the applications in the future. Now we will see the principles, operations, and determinants in this week, and later we will see how we use them to solve mathematical problems or engineering problems. Definitely, you saw this movie series, matrices or matrix. Now, matrix simply written in this way. This is the form how we wrote matrix. We give the matrix name equal to brackets, large brackets, and number inside. This is what we know, what we see for matrix. But from where it came, the idea simply is we learn in foundation, in secondary school, and even in level 1, how to solve simultaneous equations. 2 equations similar to these, x plus y equals 7, 3x minus y equals 5. This is, we call it simultaneous equation. 2 equations with 2 variables, we solve them either by elimination, by substitution. It's very easy task for us. But what if we have 4 equations with 4 variables, 100 equations with 100 variables, million, billions, and so on? I think the situations were very difficult. Elimination and substitution is not enough as a tool to solve these type of problems. So they created this part, which is matrices. They try to represent this set of equations as example using matrix. I will show you if set of equations given to you, how you convert them into matrix form. Then when you got the matrix, you will learn the operations that you can apply on matrix easily to find the solution. So later on, you will see we are going to use matrices to solve set of equations, set of linear equations, set of differential equations, and so on. This will be very easy to solve using matrices. Mike, your mic, please mute your mic. Okay, Sumaya, your mic, please. Your mic, please. Okay, thank you. So, as you can see, please, Akdas, your mic, Akdas. Okay. Please try to switch your mic, make it mute. Okay. Now, matrix, I will start from principles. Let's define matrix. Matrix is a set of numbers similar to this one. We put them between 2 brackets. Okay, in this way. As you can see, it contains many items. Okay, many items. Each item written in this way, A, I, J, where the first number I represents the row number. It means row number 1, row number 2, row number 3, blah, blah, blah. And J is the column number. Column number 1, column number 2, column number 3, and so on. As you can see, this is matrix A 1 1. It means the element in row number 1, column number 1. It's a place. It tells me the place. This is row, this is column. Okay? And each matrix have number of rows times number of columns. This represents the size, dimension of the matrix. Okay? Matrix size and dimension. So M is the rows numbers times N is the column numbers. As example, this element is element in row number 2. You see 1, 1, 2. In column number 3, this is 3, as you can see. This one, row number 1 in column number 2, and so on. So matrix have dimension which represent m times n, where m is the row numbers, n is the column numbers. Now, matrices, we can have specific type of matrices, give them names. As example, the first one, which is called square matrix. Square matrix is the matrix which have equal number of rows and columns. It means number of rows equal to the number of columns. Or we simply can write it in this way, the size n by n or m by m. It means the same, you see, the same number of rows, the same number of columns. As example, you see this matrix A, it have 3 rows, 1, 2, 3. So I write 3 times. 3 columns, 1, 2, 3. So this is square matrix. I call it square matrix. This is example. Okay. Order of the matrix, determine order of the matrix, elements of leading diagonal matrix, and elements, specific elements. Now order is 3 by 3, as you can see. 3 by 3. He asked me to find the diagonal. Diagonal, this one. القطر, diagonal. Okay? Leading diagonal matrix, it means these numbers 8, 9, 3. Okay? And he also asked me to find element A23. A23, row number 2 is this row. Element 3 is this column. So it will be 8, as you can see here. 3, column number 3, row number 2. Row number 3, column number 2, it means 6, as you can see here. 3, 3, it means row number 3, column number 3, which I can find it to be 3. Now let me ask a question here. Row number 1, column number 2. What is the value?
2.
Excellent.
5.
2, 2, 1.
2, right?
2.
Row number 1, column number 2. You see here? This is row number 1. This is column number 2. So this is my number. Now, row number 3, column number 1.
4.
Excellent.
4.
Row number 1,
4.
column number 3.
1.
Excellent. 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 Thank you. Excellent. So let's see more definitions here. Now, you see, if the matrix is m by n, which means square matrix, we call it diagonal matrix. If only the diagonal have numbers, otherwise 0. It mean. Have a look. Now, if we look to this matrix A, we see this is the diagonal. Matrix B, this is the diagonal. Matrix C, this is the diagonal, okay? Now he asked me which one of them is a diagonal matrix. Matrix A is not diagonal. Why? Because here is not 0. All numbers, other numbers excluding diagonal, should be 0. And since there is number here, so this is not diagonal matrix. The second one, matrix B, is diagonal matrix because you see here, diagonal have numbers, otherwise 0. So we call it diagonal matrix. While the last matrix is not diagonal. Why? Because there is 0 in the diagonal elements. So it's not diagonal matrix. Now, till now, I defined the matrix in general. I defined the square matrix. I defined the diagonal matrix. We still, this lecture is just to classify them, to describe them, to take examples on this and that. And at the end, I will give you exercise. I will check with you the understanding of the topics we discussed. Next lecture, we will start some techniques related to matrices and operations. Now, he told me in another definition here, another classification, the matrix is n times n, so it's square matrix, as we agreed. We call it a scalar matrix if it is diagonal and the value of the diagonal elements is the same. As example, this matrix is diagonal matrix. Square matrix first, it's a square matrix 2 by 2. Second, it is diagonal matrix because only the diagonal have numbers, otherwise 0. Okay? And at the same time, we call it a scalar matrix. Why? Because the diagonal elements have the same value. This is 2. Here it's also diagonal with 4. Here it is not scalar matrix because you see here 3 and 4, they are different, but it's diagonal matrix. Okay, square matrix and diagonal matrix at the same time. Identity matrix. Identity matrix is also square matrix, and it's diagonal matrix, and this is scalar matrix, but the number should be 1, only 1. It's called identity, only 1. So this is, as you can see here, square matrix 4 by 4, diagonal matrix because only the diagonal have elements, scalar matrix at the same time because it have the same number, but it's identity matrix because it's equal to 1. While here it is not, because it's not square matrix, it is not identity matrix, it's not square. The same thing here, it's not square. You see here, this one, the first one is 2 by 3, the second one is 3 by 2. So they are not identity matrix. Zero matrix. Zero matrix is m times n. So it's not necessary to be square. It could be square, but it's not necessary to be square. And all its elements should be 0. As example, this one. All of them are 0. You see? Negative matrix. Negative matrix. Negative matrix defined in this way. If the matrix A, as you can see here, have elements. If all elements, we inverse their signs, then we call it negative matrix. As example, if I have A and I want to find minus A, all numbers here should change their sign. This is 0, keep it, okay, in this way. So you can see here, we change the sign, positive become negative, and negative become positive. The same thing for B. As you can see here, I just need, for minus B, I just need to change the signs. Upper triangular matrix. Upper triangular matrix is a square matrix also. Okay, we have upper triangular matrix and lower triangular matrix. You can see here that this matrix A, we call it upper triangular matrix. Why? Because from the diagonal, the numbers are above the diagonal, and below the diagonal should be 0. You see here, these are the numbers, upper, and below the diagonal should be 0. We call it upper triangular matrix. And lower, it's clear that it should be 0, should be the upper side, and the diagonal above the diagonal. As you can see here, these are the number, and 0 should be above the diagonal elements. This is called upper diagonal matrix and lower diagonal matrix. I think until this point, clarification, the definitions, their explanation is clear. We define matrix, square matrix, diagonal matrix, scalar matrix, identity matrix, zero matrix, negative matrix, and upper and lower diagonal matrix. Transpose of matrix. If you are given any matrix in this way, as example, A, I, J, I row, J row, then A, T, transpose, without negative, A, T transpose of the matrix, mean it will be A, J, I. It means we change I into J. Okay? Let me show you how. I am given here square matrix A. Now I want to find transpose of this matrix. The first row will be changed to be the first column. The second row will be changed to be second column. Third row will be changed to be the third column. Definitely this matrix is a 3 times 3, so when we change them, the size is not changed. We keep it. But this matrix is a 3 times 2, because as you can see here, 2 rows, 3 rows, 2 columns. So when I change them, that will be the new matrix 2 by 3, the transpose. See this one, see this one. This row, first row, will be first column. Second row will be second column. And third row will be third column. So you can see here 3 times 2 as we discussed. Clear the transpose? Is it clear?
Yes.
Yes.
Great. Great. Great.
Yes.
Great. Now, symmetric matrix. Symmetric matrix is also square matrix, but it's the matrix and its transpose is the same. As example, this matrix A is a square matrix and it's symmetric matrix because when you rotate it, you have the same elements. As example, you see this row will be this column. This row, this is transpose, will be the second column, and this row will be the third column. If I look to the two matrices, A and its transpose, I will see that the elements are in the same places, 4, 2, 3, 2, 5, 6, 3, 6, 7. The same here, 4, 2, 3, 2, 5, 6, 3, 6, 7. The same places. It's not changing. So for that, we call it symmetric matrix. Skew matrix is also square matrix, skew, okay? But what happened is when we take the transpose, we found it is the negative of the matrix, okay? As example, this matrix A. When I take this one, this row, it becomes the first column. Second row, second column. Third row, third column. And when I compare between A transpose and A, I can see 0, 0. 1, it become -1. 2, it become -2. -1, it become 1. 0, 0. Oh, it's the same elements in their same places, but with different sign. If it is positive, it become negative. Negative, it become positive. For that, we call it skew matrix. Row echelon form. Row echelon form, the matrix, we call it row echelon form if we have any matrix m by n, okay? And it satisfies 3 conditions. What are these conditions? I will discuss them now. I want you to focus with me. I'm around to finish. So we will take exercises to practice together. Have a look. I will read and explain. The first condition, all 0 rows, if any. It's not necessary to have 0 rows. We may don't have, but if they are there, then they should appear at the bottom. I mean, as example, you can see here, this is row with 0 values. It should appear at the bottom, not in the middle, not in the top. You see here, this is row with zeros. You may say, okay, what about A? A have no row with zeros, so there is no problem. Now, all these 3 matrices A, B, C satisfy the first condition. We don't have problem with the first condition, so it's there. But we cannot say that still. We cannot say the matrix is row echelon form. We need to satisfy the other 2 conditions. We have 3 to satisfy. The second condition. This is done. Let's come to the second one. The first non-zero row, 0 entry from the left of a non-zero is number 1. This entry called leading one of its row. What does it mean? It means the first non-zero, it means the first row. The first row, okay, should start with 1. It could be 0 then 1, but it should not start with any other number. 2, 3, 7 million, whatever the number. No, with 1. Sorry, with 1. It should start with 1. As example, this one is okay, this one is okay, this one, all of them, A, B, C. Now, the third condition, also we need to satisfy to say this is row echelon form. For each non-zero row, the number 1 appear to the right of the leading one of the previous row. What does it mean? I mean, have a look here. This is the leading row, the first one. Let's start with 1, it's okay. But the second one here did not satisfy the last condition, condition number 3. Why? Because here it started with 1 on the same age. No, it should be delayed. Here the 1 should be, this should be 0. So this did not satisfy the third condition. This one satisfied because you see here, This is the first row, it started with 1. The second row started with 1. 1 order behind. It means here 0, here should be 1. This one started with 1, as you can see here. And this second row started with 1 order behind. So it satisfies the third condition. The third row also 1 order behind, and so on. You need to return 1 step behind and start with 1. So you satisfy the third condition. As you can see here, this one, the problem here. The second one is okay. Yes?
Can you repeat the symmetric matrix?
Please repeat your question. It's not clear what you are saying.
Can you repeat the symmetric matrix?
Symmetric matrix?
Yeah.
Oh, we cross it. Okay. Symmetric matrix. This is the matrix. When we do transpose, it means changing row into columns. The element will appear in the same places. As example, this is the transpose. Okay, let me change the color. You see 4 is the first item, I11. Here A12 is the same, which is 2. A13 is a 3 in the same places, the same values in the same places. For that we call it symmetric, because when they did the transpose, their values never change their places, in the same places. Okay?
Okay, Doctor.
Row echelon form. As you can see here, the problem here happened in this number, but here we satisfy the 3 conditions. See as example, zeros came at the end. The first row started with 1. The second row started with 1, but 1 place behind. Okay, so we move here. Should 1 started with 1 also, and so on. Now, reduced row echelon form, the same previous one, but we call it reduced row echelon form. What is the difference? Okay, the same previous 3 condition should be applied, satisfy. Okay, plus 1 more condition. What it say? If a column contains a leading 1, then all other entries in the column are 0. What this mean? Have a look. Have a look. Now, if I come to this one, the first one here is row echelon form, reduced row echelon form. Why? If we have zeros, we don't have zeros, so we satisfy the first condition. The second condition, the leading row start with 1. Yeah, correct. It started with 1. The third condition, next in rows start 1 order behind, 1 point behind, 1 step behind, and with 1. As you can see here, the second row started with 1, here started with 1 and 1 step behind. And the fourth condition we added to say that this is the reduced row echelon form is only the diagonal now, the row, let me say the ones leading the rows will start with 1, otherwise zeros. You can see here zeros. The second one is also row echelon form because we satisfy the 4 condition. But the third one, yes, there are zeros here and here, but here is -1, it's not 1. It's supposed to be 1. So we say this is reduced row echelon form. Now, one more point here, before I go to exercises, is if I have 2 matrices A and B, okay, then we will say that A equal B only and only if each element equal to the same element in the same place for the next matrix. It means, as example, here P, he told me P, which is this matrix, equal to Q, which is this matrix. I equate between them. Now, these 2 matrices are equal only if this element equal this element. This element equal the same place. So 4 equal x, 0 equal z, y equal 5, 3 equal 3. Then we say these are equal matrices. Now let's see the exercises. First of all, tell me the dimension. This matrix, what is the dimension for the first matrix?
Three into two.
No?
2.
3 to
multiply
3.
3.
Excellent. 2 by 3. You see here? You see? 2, 1, 2 times 3. 1, 2, 3. What about the second matrix?
3 to 3.
3 to 3.
Excellent. The third matrix?
1
2.
to 2.
2 to 1.
2 to
2
1.
by 1. 2 by 1. 2 times 1. Okay. What about the fourth matrix?
1 by
1 to 2.
Excellent.
One.
Excellent. Well done. Well done. Well done. Now, this matrix A is symmetric matrix. Okay? It's symmetric. What do we mean by symmetric? Do you remember?
Yes.
What do we mean by symmetric matrix? When
The
you
same.
said
The same.
the same
And the
what?
same value.
For the transpose, right? It mean
Right.
A
Yes.
equal 80. Okay? Right?
Yes.
Great. Then find 80, and then equate them to find A, B, C. Do it. Do it. I will give you a couple of minutes to solve it before I start solve it. How much A?
2.
2.
2.
Excellent, excellent. So let's solve it. Let's solve it together. Okay. Now this is matrix A, and this is matrix A transpose. So when I work on it, it will be 1, 2, 3, A, 4, 5, B, C, 6. Right? Let me change the color. Oops. Okay. Now we are looking for A, right? A is supposed to be equal to 2 because we say it's equal. We mention equal, it means each element should equal to the same element in the other matrix. B should equal to, C should equal to 5. And so on. This is clear?
Yes, doctor.
Okay.
Yes,
Now,
Can you repeat?
yeah, okay. Now, he told me symmetric matrix. The definition for symmetric matrix is A equal A transpose, correct? Okay. So I did the transpose. The first row, or let me work here. The first row becomes the first column. Second row, second column. Third row, third column. And since we have equal sign here, then elements should equal in the same place. It means this element, which is A, it is 2, 1. It's the element order is 2, row 2, column 1. And the same thing here. 2 is the element in 2 column 1. So they should supposed to be equal. This B is supposed to equal to 3, and this C is supposed to equal to 5. Clear?
Yes, doctor, it's clear.
Okay. Now, almost the same idea, but for skew matrix.
Clear.
Okay. From the definition, we understand what the skew matrix is. It means when we did the transpose, become minus the matrix, original matrix. So do the same mean A equal minus A equal A transpose, right? So do the same to find A, B, C. I will keep this to you as exercise, solve it at home because it's easy. It's 2-3 steps. But let me go to the last one here. He told me name the following matrices. So what we call this matrix? You tell me.
Our triangle matrix.
What we call it? Type of matrix here? Upper triangular matrix. Correct. Yeah, you are correct. You are right. Is there any other name for the matrix? Also, it is square matrix, right?
Square matrix.
Excellent. Excellent. What about the second matrix here? What we call it?
Upper triangular
Excellent.
matrix.
What about the third one?
Lower.
Excellent. What about this matrix?
Also lower.
Also lower triangular. So now, let me summarize. Today, we define the matrices, from where it came, what is the point behind matrix. And we mentioned that later on we will see we will use matrix to solve easily set of linear equations, differential equations, mathematical problems. Okay? And we define different type of matrices. We classify them into square matrix, symmetric matrix, skew matrix, transpose of matrix, diagonal matrix, scalar matrix, upper triangular matrix, lower triangular matrix, row echelon form, reduced row echelon form, and equal matrices. Now, next session, we will discuss the operation of matrices and we will start with the determinants. After that, you will see with weeks, we will add more topics. We will see how we do inverse of matrices, how we will solve set of linear equations using Gaussian elimination, Cramer rule, different type of techniques, eigenvalue, eigenvectors, differential equation solution using matrices. So we will take them step by step. But until this point, today's session is just to define the topic, what is it about, what are the different type of matrices. Do you have a question until this point?
No.
Okay, then I will stop recording here.